So last time I assigned homework. I want to know if anyone did it. Great, a wonderful class. So I hope you will consider doing this as time goes on. And just remind you, the homework was to think of what are the very best experiments in all of science that you just admire because of the essence of the experimental technique, right? And what it was, either it's because of the simplicity, because it nails the question, because it's expensive, because it's cheap. You have all of these options to think about, and you should think about, well, what is it that makes a good experiment, and which are the ones that you admire. And so I'm emphasizing this because this has been mostly a theory summer school from what I can gather, and I want to bring the essence of experiment to these classes. And so that's what my 3 lectures are going to be about, have been about talking about the experiment per se, not so much what the subject of the experiments are, but the experimental aspect itself. So in the last lecture, I talked about 2 experiments. And so the first one was meant to show how some ideas from simple flow behavior can then, just thinking about those, can be applicable to systems that you wouldn't have thought at the onset should be involved in that kind of behavior. That is, you wouldn't have thought that thinking of a flow of a river down a mountainside would be relevant to, let's say, electrons flowing in a metal. And so that was what I was trying to emphasize. Oh, some of these same ideas come back and forth. But so that was one reason I brought that up. Another reason that I brought that up was, talked about that experiment, was because I kind of emphasized, well, this is really trivial physics in some sense. I mean, nothing's ever really trivial, but it's trivial enough. And you might have thought, well, there's no reason to do the experiment because it was so simple. I mean, obvious had to be this way. But then when you do the experiment, because nature has other things in mind and has other plans for how things should behave, you actually learn something about the material and about the way of doing the experiment that you didn't know before. And so there was a big surprise that came from that it took us a long time to try and figure out how to even think about that. The second experiment I talked about was, again, a tabletop experiment. And so this very simple tabletop experiment, what I wanted to show about that was, well, it had a surprising reach in that we could think about this in terms of this simple tabletop experiment. There's grains of sand coming out of a tube, but that when you start looking at that in detail, you realize, oh, this is not so different from other things which are really quite far afield. That is, so we made the parallel between the grains of sand hitting a target and the quark-gluon plasma. And so those experiments, and that those things were really part of the same flavor of things, and that one actually could tell you something about the other, and that there was an interaction between these two. And so that's kind of the part that I love about that experiment, is it, simple as it was a classical analog of one of the major experiments that are going on in particle physics today. So, and then the other part about this was that once you look at the results of that experiment, it makes you realize, oh, you can ask rather basic questions about what it means to be a liquid. In this case, that was what we were interested in, but also what it means to be in equilibrium. That is, we had this very small interaction region, And you want to think that, oh, that's kind of an equilibrium system, but is it? And by just this simple experiment that we watched, we could see that the particles were actually, some degrees of freedom were in equilibrium and others were not. And so it shows the complexity of this and gives us a kind of a foothold into those kinds of questions. So today I want to change topics. Again, not because it's the topics that you should be so involved in, but it's the experiment that I want you to be thinking about, and what you can learn from an experiment, and what doing the experiment teaches you, and why doing the experiment is such a I don't know if I can use the word here, such a pleasure. I mean, this is the thing that I want to get across. Okay, so what I'm going to talk about is material failure today, at least the first part of this talk, and I want to do a little bit of talking about some issues that come up in that. And so, and again, what I hope is that you'll see that the connections come in at, to different scales. Again, this is conferences called hydrodynamics across scales. This is something that I hope will also cross scales. Yeah.
I just wanted you to know that the students have set up a written experiments channel.
Oh, thank you. Oh, yes. Okay. I'm so happy. I'm okay. You'll have to teach me how to use the computer to do that, but it's okay.
I have a question actually about that. So where does observations fit in this? Like, I think about Galileo's observations of the Galilean moons of Jupiter. How would you, is that an experiment?
Well, look, I mean, I do think that observation is different from an experiment per se, because the experiment, you have to, you get to manipulate things to do it. But I have to say, I mean, if you were going to, I've been trying to think about what are my favorite things, and one of them, close to that, was Romer's measurement of the speed of light, the first measurement of the speed of light. I mean, how did he do that? I mean, that really just blows me away. And that's observational, right? That was looking at the moons of Jupiter, I think it was Jupiter, and measuring those carefully. But it was a way of understanding something there that, but that really is an observational thing. But to me, that at least, look, it's a gray area, obviously, but it has a bit of a flavor of the experiment as well, because it actually measured something quite concrete. But we can certainly talk about that a lot. I mean, but I do think of observational stuff as different. So if you look at seismic activity in earthquakes, well, it's not really, you set up things to measure, but it's not, you're not manipulating it in the same way, and so that makes a bit of a difference.
Is the element of surprise, though, that can still...
Yeah, I mean, so look, this is not putting down observation, and it's certainly not putting down theory. It's just I want to, you've all had theory. I think you've had theory for 3 weeks. Okay, so you've had a lot of theory. So I want you to see an experiment. Okay, so I said I was going to talk about material failure. So I want to just take this sheet, and I'm going to pull it apart. Oh, shit. These are my notes. Okay, but they're my notes. But what you can see from this is that I pulled this thing apart, and I got a tear that went from one side to the other. And that was what you get from pulling the sheet apart. And so if you look in the literature about fracture, about how materials fail, there's generally two categories that they try to put things in. One is this brittle fracture of this, where the thing just tears apart, that you as the thing crack propagates, the stress gets focused to the forward part of that crack as it propagates, and this helps move it along. The other thing that they always talk about, and this is the only other thing they really talk about is ductile failure. So there's always brittle as in contrast to ductile. And so here is ductile failure. So I have a just this piece, and you can see that it's not tearing that same way. It's not brittly fracturing. It's just somehow smoothly deforming until it goes to the region of failure goes to zero and this thing falls apart. So you've all seen this is just silly putty that I bought specially for this conference, so I'm going to hand it around so you can see this. Okay, so why do I talk about those two things? Is because the types of examples that I'm going to talk about today, at least to my mind, I don't know how to fit it into that picture. And I mean, even though that, you read the books on fracture, that's how they all seem to want us to think about these material failure. I just get totally confused about this. And so I'm not trying to tell you, oh, I understand the answer to this, but I am trying to tell you, oh, we've got to understand these phenomena as well. So that's the aspect I want to say. So I'm going to start off with some work that was done originally a few years ago. This was when Vincenzo Vitelli was still in Leiden. He's moved to Chicago since then. And this is his group of theorists in his group. And then there were experiments that were done by Michelle Driscoll in our group. And that they complement each other, these two things. But because what my job is today is to talk about experiment, I'm going to be concentrating very much on the experimental aspect of this. But yeah, I mean, the experiments are well. We'll see. We'll see how where you can go with this, but what I can say is that experimentalists are so efficient that we can do it all. Okay. So I'm going to just start with this movie, which is what we have here. We saw the brittle ductile failure. What this is a real experimental movie you're going to see. This grayish area here is acrylic. And it's just cut out in this form on a laser cutter, so that this is a thin sheet of acrylic, and it's being pulled from below and above in this direction. And these are, hexagonal honeycomb lattice type of structure, and it's not ordered. There's slight disorder, that is, so these things have been moved around a little bit, something like 10% from their initial position. So it's somewhat disordered, but it's basically this honeycomb lattice. And this is filmed, crucially, at 91,000 frames per second. And it's shown back to you at what, 30 frames per second, something like this. Okay, so this is the speed at which it goes. And so what you're going to see as it pulls apart, this is going to fail, and you're going to see colors on certain bonds here. And those are the bonds that are broken. That came in afterwards. We went in and colored, so you can see which ones came first, second, third, fourth. This is probably about a half a centimeter, something like that. Okay, so now we let this go, and so let's watch this. Okay, so this is brittle fracture, right? That is, you got to see this go, and you only got to see it go because we were filming it at 91,000 frames a second, and even so, it went across pretty quickly. And if this had been solid, it would have gone even faster, I think, but it would have been close to the speed of sound in this material. But this interrupts it, so it's a little bit slower than that. But it's it's a fast process, and it's a thin process. That is, it's not spreading out over this whole material. So now I want to do another experiment, And so I'll play this one again just so that you see it. But this was at 91,000 frames a second. And this one is going to be framed at 30 frames a second. So much, much, much slower, thousands of times slower than this is just the original rate at which the filming is done. These two lattices are identical. There's the same acrylic, same thickness of the acrylic, same honeycomb region of this, and in the same shape. The only difference is that we've made these pieces narrow, right? This is thick, stubby stuff. This is thin, well, not unstubby stuff, okay? And so let's see the first one again. Okay, so that was how fast that one went across. And now let's see the second one. And this is, again, remember, it's thousands times slower than the first in just the filming speed. Also play back at the same rate. Still going. Okay, so finally broke apart. Okay, so look, this is incredibly much slower. I mean, just the filming speed was several thousand times less. Whatever is it, 30,000, 3,000 times less. But then this took 15 seconds to play, and this was in less than a second it went across. So it's really slow. Something else goes on with this is, if I just showed you this picture, this went across in a narrow region, and this one is spreading out over the whole thing that you saw. This one come first, and then something down here, then some stuff here, then back and forth. It went all over the place as it started to break apart. So something is really different just by changing the thickness of this behavior. And what I want to kind of emphasize is, look, when you think about brittle fracture, well, this is brittle fracture. We kind of know it when we see it. It's fast, it ruptures across. Nothing has a chance to change. And why not? Because the speed of sound in this is faster than any other thing in the material. And so nothing else has a chance to do any rearrangement in the time it takes for this thing to rip across the sample. So is this a ductile fracture? And the answer is no, it can't possibly be, because there's no rearrangement here, right? This was just, it broke and didn't rearrange. It didn't try to find some better place to do it. It just broke. It didn't, the rest of the material didn't ooze its way the way your silly putty that you're passing around is doing. And so it's really quite a separate behavior. Now, I'm putting this because I think this is kind of in your face, amazing thing. Right? But I also want to say, I don't understand it. I mean, I don't have a theory for why this is so different from this. But what we did with this experiment was, well, I told you that there was a lot of simulations that were done. And so there were, this is just what we saw from the experiment, the top two. But the two bottom sets are, both of these are just network lattices that are, in this case, this was basically based on particles that have been pushed together until they jam and overlap, and then you replace the particles by nodes, and the particles that are touching you replaced by some little strut between them. And then you watch this thing get pulled apart, and there's no dynamics in this. This is just ask which bond is under the most stress as you pull it, and you break that one. Then you break the next one, and then you break the next one, and it makes this rather clean sweep across the material. When we do this, but starting with a much lower number of contacts, still above, it's still a jammed system, it's still above the ISO. I'll tell you a little bit about jamming in a second, but it's just many fewer contacts to start with. You can see, this one is now beginning to be very diffuse. That is, you can see them all over the place. This thing is failing. At the bottom, this is just a square lattice with cross braces. And with the cross braces, you know that a square lattice would have been very, you could always have sheared this easily, but if you put enough cross braces in, you make this rigid as well. And when it's rigid, you get this thing going across. But when you have many fewer cross braces, and this thing becomes almost ready to go, it's still stable against that, but it's not as overly cross braced as this one. It starts to flow all over the place. So this is that kind of behavior. There's another simulation which is related to this, and this was really on jamming. So I have to just take a step away for a second to say what it is that was done here. And so when you take a jammed system, what you do is you take a bunch of spheres on the computer and you squeeze them and squeeze them and squeeze them until they just begin to touch. And there's wonderful things about the jamming transition that I won't talk about here, but when they just touch, then there's special things about how many neighbors each particle has at the touching point. And so once it's just become rigid, you have exactly Z equals ZC is 2 times the dimensionality of space at that point. So this is just what's called Maxwell counting. The thing is, I don't want to go into it too much because that's not the point I want to talk about here, but it's the same behavior. So what these experiments were done were taking this 2-dimensional system and squeezing it in both directions. And here's where we are, a regular solid. So this is very far away from that transition where this thing is very far from losing rigidity. And you break these bonds and you get this really very classic behavior of you get cracks forming everywhere as you start squeezing this thing. But as you change the number of bonds that you start with, the cracks really are getting wider. I mean, there are big regions where nothing happens, but then you get these cracks that have a thickness, and you can measure the thickness of this. They're fairly clear what the thickness of these failure regions are. And then you get very close to the transition, and this failure zone now is the size of your sample. Okay, so this is something, I don't know what to call it. We've called it distributed failure for lack of a better name, but it's, it is something where the failure is occurring, over, not in the ordinary crack propagation, and also not in the ductal region because we're not allowing anything to rearrange. Yeah.
Once again, can you repeat what's the deformation applied?
So this one was just uniform compression. And what we did here was, again, the same, the bond under the most stress we take away. And so that's the, no, the volume changes a little bit, but not by enough. That is, we're not, this is all, we just do it a little bit and ask which particle, which bond has the most stress on it, and we remove it. It's a simulation, so we can do it. So we're not changing anything much at all. You can just ask as you change it by 0.1%, and you just measure what the stresses are on each bond, and you keep doing that over and over again. Oh, those are which came first and which came second. I mean, so it's just a way of encoding the time in this. Okay, and so this was done by a Carl Goodrich and Julia. Okay, so this is, your hand is not up, your hand is just playing with, okay, good, I just want to make sure it was, given this, I mean, this is, somehow a fact that doesn't fit into my view of what I've been told about fracture in any case. It seems to be somehow different. But so I kept my eye open for other examples of where you might see this. And so that's what I want to now turn to now. And so this is work done by a current graduate student, Kai To, who has just been working on this. And this is has the title that we're calling Rifts and Rafts. And so what we're going to do here is we're going to take a bunch of particles and spread them out on top of a liquid bath. And the particles have some weight on them. So let me, they have some weight on them. So what they do is they deform, I mean, so there are two things. So I guess it's on the slide, but just, so if you have this water and I put a particle on here, it's going to sink down until it's partly submerged. As it's partly submerged, the liquid remains contact with the particles at some point along their circumference. And so that bends the water up on both sides. Okay, so this is what the shape of the water interface is. It kind of dimples as you go down into that case. If you have another particle over here that also has this, you'll see that, oh, they're going to attract each other by some small, because this region is a little lower and the gravity and surface tension is going to try and pull these things together. And so these two things will feel an attraction. Okay, that's the idea behind why these things form a raft in the first place. And it's known in the community as the Cheerios effect, because this is what you see in a bowl of Cheerios when you have your two things of Cheerio particles, not particles, bits. They're the two bits of Cheerios sitting there, and they will slowly get pulled towards each other. And so this depends on what's called the bond number in the material, so in the system. And the bond number is just basically the gravity effect of buoyancy on this side divided by the surface tension holding it up. And so it's a dimensionless number. And what this is saying is that it's basically the diameter squared or radius squared of the particle divided by the capillary length of the liquid, which is just basically gravity fighting surface tension here to keep this thing buoyant. Okay, and so this is the idea of how the experiment, why you get a, if I can find notes that aren't torn apart. Okay, this is what we see. And so what I want to show now is what is the experiment that Kai has been doing. And so this is a photograph of it, but this is the just the schematic view of it. So you have a bunch of these small particles, and you have what we call pullers at both ends. And what you do is these particles are attracted to one another in this region, and they are pulled out in both directions, or one direction. You can do it either way, but this way is symmetrically pull them out in both directions. And this stretches that raft of particles apart. Okay, and so this is, and then you have sidewalls that's holding this thing in, and we'll talk a little bit about the interaction of the puller with the particles in a second. But so what do you see? And so this is now a movie that Kai took of her system, and I'm going to play it. Whoops, that didn't play it. Let's see, how do I? Maybe this will play. That's not very nice. I'm supposed to hold. So let me just try to do it. Is this? Okay, so by hand, you can see how this thing pulls out. And what I want you to see is, this is again an example of failure distributed through everything. And it's the green and blue are different size particles that you used to keep the thing from crystallizing on this surface. And you see this whole set of rifts in this raft, okay? Now, oh, it stands there, okay, good. Okay, so what's the other thing I want you to notice about this? Okay, so it is, all of these rifts have formed. It seems to be an example of what of distributed failure in the same kind as I said before. But the other thing that I hope you see is, I think this is just lovely. I mean, I just think this pattern is something like, I haven't seen this pattern before. And where have I seen this pattern? I mean, it somehow is very appealing to the eye. It grabs me viscerally whenever I see this. And as I said last time, when I see something in nature that's, viscerally grabbing me, I want to understand it somehow. And so this fits in with our research plan, so that's great. But it also has this other aspect, which I don't want to go I don't want to go neglected in this audience. Yeah, so you had a question. Yes. So this is water underneath, and these are just these it's just a water surface, and the water can come in from underneath to fill this up. So it's not, I'm not making anything fall down in here. I'm just pulling the surface of this water along. I will get to that. Talk about it. So these are about 500 microns, something. That's a scale. And so some will be a little bit bigger and some will be a little bit smaller. That's what the different colors are. So some are 600, some are 500. Some are.
By any chance, there is an interaction between the walls that are included in particles?
Yeah, yes. So I'm going to talk about that in a second, because that's also part of what I need to tell you about how the experiment is done. Okay. So let's see. I'm going to delay those two questions for just a couple of minutes, but I will get to them. And if not, then hammer me again. But what I just want to say is, so how, as a condensed matter physicist, have I been taught to look at this? Well, what I would have been, okay, clearly I should be able to get the important information out of this by looking at the pair distribution function. That is, if I take any particle as the origin, I ask what's the probability of getting another particle, let's say in the x direction or in the y direction or any direction between here. And so this is going to be g of x, y is equal to 2 v over n squared. This is all normalization stuff. Okay, so this is the definition of the pair distribution function. It's what you look for in crystals. This will tell you where you have the crystal peaks in real space. And it's what you look at in glasses when you see, okay, I want to find out what is the, with one particle as an origin, what does it look like in my vicinity for where the other particles are located? And I just get something about what the density of the particles are if I go far enough away. So this is one thing I could look at. The other thing, which would be to look at the structure factor. And the structure factor would just be S of Kx and Ky. And notice I'm separating X and Y out here because I'm only pulling in one of these directions. And so they may be different in the two. So I don't want to just take a radial average. So this would be the standard thing that you would do to look at the structure factor of the material. I mean, so these are the, what we're taught to look like. And so I put that down because that's the first thing we did. I mean, this is what we, how do I distinguish this from other patterns that I see in nature? And
Sorry, the way you've written that, just separates, right? Some arrive, some multiply by some of these.
yeah, so that's right. It's just going to be, so I will see things in two different directions, whether I'm in the X direction or the Y direction. Right? And so, so these are what the patterns look like. And what this is on this side here, this is what happens at initially before any pulling has gone on. And over here is what happens after you've strained this thing to a strain of 1 in this. So it's moved out as much as the original length. And I don't know about you, but I can't see a whole lot in here. It doesn't really capture the essence of what it is that we're interested in. Yeah, there's a little something down here at small k in this in the structure factor, but that's it's not capturing somehow what what excites me about that image. The other thing that I could have done, or which Kai did do, was try to look at analyzing the various cracks in here. What are the shapes of these cracks? And so how do you do that? I mean, in this random system. And so her idea was to stick, false particles in here. That's how many particles could I stick into this region? And that would somehow define the size and the shape of this crack. And then you blur it out and you get a kind of ellipses that you can take a look at. And you don't, again, this says something about what the shape of those rifts are, but it doesn't give me very much information about this global scale of what this thing is looking at. Okay, so now I'm getting on to what the experiment turned out to be. And so this, I hope, answers the questions that you had. So the first one is, what are the boundary conditions at the pullers? Okay, so these are the particles, the raft of particles, and you can, so you have your acrylic puller that you're going to be pulling, let's say in this direction here, and you can locate this, either submerge it or pull it up. But once you have this contact line pinned at this puller, then you get to define what the boundary conditions are. So if this is a little bit raised, it's repulsive because particles are going to be flowing away from that puller, and so they don't want to be next to it. And so I can just pull this thing out, and that's a repulsive boundary condition. Likewise, I could have made this attractive by submerging this. And so they'd be attracted to there, so they fall towards the puller, and now I pull that away. And that's attractive, and so that's holding on to the. So this is the what I get to do with that. The next thing, well, suppose I just use the repulsive boundary condition. So I'm not holding onto the raft at all. I'm just letting I'm pulling on the fluid and expanding the fluid in this region, and I want to see what happens there. So we hold them in with side rails, I should say. I think maybe that was your question about the sides of this, but those have repulsive boundaries so that we're just always trying to let it not go up to the edges of the container. So what we want to look at here was, well, how does the fluid surface change as I'm pulling these things? So this has nothing to do with the particles in it. This is just, we put tiny little grains on the surface that are very far from each other and measure the PIV, particle something velocimetry, to see where these things have moved. And what you see is that all this does, as you pull this apart, is it expands the fluid uniformly around this thing. It's basically, the way I like to say is it's just expanding the metric of that surface in that one-dimensional direction. Okay, and so this is now measuring how the particles, how the surface is flowing in from one side to the other for all the different velocities we use. So this is something about where our system is located, how we're going to be deforming the system. So then the $1 million question, or whatever number question, okay, $50 question, is what's the speed at which we do this, right? So someone asked that, and so let's hope this works. So we do this now at 3 different speeds. So this is with repulsive boundary conditions. We're going to be moving the pullers at v equals 2.5 millimeters per second. And then we can change it by a factor of 10 each time. And so let's see what we get. So when we do this slowly, this thing doesn't really change. It's stationary, it didn't deform much. Okay. Now I should just point out that this is the rate at which it's being done. It's not being filmed at that rate, so they're going to look more or less the same. But this is going to be 10 times faster than that, and this is 10 times faster than that. So now we do it at 20 millimeters per second. And so now you see it does elongate this thing, it pulls it apart. And you're beginning to see all these holes opening up in this region here. And so that's where it's beginning to become beautiful. Okay, and so now the third one is at 200 millimeters per second. And so now you see that this thing has this, but on steroids, right? I mean, it's very fine structure in this behavior. And so this is the, shows that your question was very prescient about what velocity did I do this at, because changing the velocity changes the structure dramatically. And so this is the new thing coming into this.
First, understand the PIV experiment. The result shows that there is like a uniform expansion of the interface all over the system.
Right.
Just make sure. Okay.
That's
So
all. That's what's driving this. It's not being held at the edges anymore.
Okay. Perfectly. Okay.
How does the effect that we see here depend on fluid sources? Are they important?
Well, there are some. So the fluid flow that he just was pointing out, that's the most dominant thing, just pulling out in both directions. There is some stuff around the edges of this which are near the pullers, and so because there's flow backwards around, and so that's we try to minimize that, but that's so you see the edges are always a little bit different from from the center, but that thing is due to those secondary flows.
But imagine that instead of particles, I will just put some colorants there, molecular colorants, who would say something.
Yeah, that's the idea. Okay, so this is what we have. And so these are before and after for the different velocity of, well, I'm sorry. This is low velocity, this is a high velocity, and these are different strains along the way. There's a different, we just took frames at, instantaneously at the beginning, middle, a little bit farther and a little bit farther. And what you see is that very quickly, this thing decides what it wants to do, and it kind of stays in that behavior. This is three blow-ups of what that structure is. And what you see is this is very compact. It didn't change from the beginning. All the holes you see here are just because you take disks in a plane, they don't pack, they don't tile space. And so they have to leave little holes between them. And so this is going to be a problem for analyzing this. But once you start pulling it a little bit faster and you see these things begin to open up, you can begin to see the spacing increase. And then here you see that this thing is really single particle behavior throughout. So how do we get rid of the these little holes in here? And so this is a technique that's well known in image analysis. As if you want to see this, what we do is we take each of these. First of all, we threshold it so we get black or white, and then we expand all of the particles by something like their, so that if they were squares, they would then all be touching each other. And so you expand them, and then you just look at the perimeters of what's left over, and you return that back to where it was. So all the individual particles are expanded, and then if they are not touching anything else, they will be brought back to the same size. But if they are touching something else, only the edges of where that exists will be cut away. And so this is what you see. So when it's dense, you apply this and you see that there are a few things that remain afterwards. This is from the original case, and so it's not, there are relatively few defects that you see. Then you apply this for a less dense system, and you can see what kind of shapes you get. And so this white is a contiguous area where the material is touching. Okay, so how do we then try to analyze this? Well, we want to ask, how big are these rafts? Not the rifts, but the rafts. Okay, and so what we do is we raster scan this in the X direction. And so so here we would have had trouble because we have all those black spots. But here, when we have all of this kind of white area, we just take one line through here. And once it starts here, we just count how many white spaces we have until we hit another black space. And so we keep track of this for every line through here, going through the whole system. And so we can get a whole system of what the statistics are of the sizes of these rafts in this X direction. And so as you would expect, you see a change in this. So this is where we're going very rapidly. And so when you go very rapidly, what you see is all of the raft things are basically just one particle wide. They don't get to be more than that because they get pulled apart. The ones that are very, very slowly, basically everything is at the size of the system. And in between, you get some distribution of this. And you can then ask, well, how does the average of this behave with the flow? So we can do this at different angles, and the angle doesn't seem to matter very much. So statistically, these rafts are the same independent of what angle we're looking in, within 10% is basically behavior. So we can then do what we're waiting to see, which is plot the average of the raft length, raft size, versus the velocity. And you see that At low velocity, the raft is big. At high velocity, the raft gets smaller. But because of the size of our system, it can never get smaller than a single particle diameter. So we're cut off by this red line here. And it can never get bigger than the size of the initial size of the system. So we're cut off there. And so there's an interpolation function that we have between those, but with a power law in the middle. So this is the form with which we try to look at the data. Well, everything. So this is divided by what happens at 0 degrees. So everything has to be there, and then it's okay. So we look at two different fluids. So this is for water, and then we want to change the viscosity a lot. So we use the water glycerol mixture for as another bath to look at this and to see how these things change. And you see this looks kind of the same, but off to lower velocity. So how do we think about understanding this? And so the idea here is I'm just going to let me turn this off so we're not blinded by all of that. And just what is the idea? So the idea is a 1D model. And we have particles in a line. And what we ask is, okay, let's just set up the equation of motions for this system. And the first thing that we know is that these particles are overdamped. So the left-hand side is going to be V sub I, which is equal to d ui dt. So that's it's not going to be acceleration, but just, and so it's just the velocity is equal to the force pulling on it. And I'm going to put in a constant that takes into account all the viscous damping on this side and so forth in a minute. But this is then equal to getting all the forces right that you get from the Cheerios effect. So I'll put some constant here, which takes into, puts all sins into this constant. And then what we write here is how does the important thing that we should understand about the Cheerios effect, what is the nature of the interaction? If this were springs, the farther this particle is away from me, the stronger that force is. But in the case of the Cheerios effect, the force is going to be stronger here than out here because the curvature of the surface is getting weaker and weaker as you move away. So the idea here is, the force now is not going as the stretching of the spring, but 1 over the stretching of the spring. And so this is going to be 1 over delta x j plus 1. And so what am I doing here? So I'm just saying it's the force on this particle is the force from the spring on the left, which has this particular form, and the spring on the right, which has that particular form. And one is pulling to the left, the other is pulling to the right. So that's why one has a plus sign, one has a minus sign. And we just then expand this. So this is precisely how you get phonons in a one-dimensional model in Kittel if you do condensed matter, a solid state where you use real springs, not 1/over springs for the 1/over the separation for the separation, and this would have been the acceleration, right? But those are the two main differences. So you can expand this, and so this is going to be 1/over delta x, which is the average separation that it starts from, plus u of x of j plus 1 minus u of x j. So that's the, yeah, we're just saying it's where it was, plus this little bit of change, how much the particle on the left moved versus how much I've moved. And so so this is the spirit of what the calculation is. You work this through. So now it's just a question of making sure that this is small compared to delta x. So this is the initial behavior of this material. And what you have is at the end that this is equal to, so d u what do I want to say? Du of x j d t is equal to d times 1/over delta x squared of 2u j 2u of x j minus u of xj plus 1 plus x j minus 1. So this is just minus del squared on this side. So the end result is that d u d t is equal to minus d del squared. So it's a diffusion equation, but with a negative diffusion coefficient. And yeah, so this is the so I'm trying to give the flavor of what this calculation is. As I said, all the bits and pieces are on the d value of that. We can evaluate exactly what that is, and we have. But and maybe I can give you an idea of what that. So you want to know what d is? D is equal dimensionless numbers times d to the fifth, which is a particle size, rho g squared divided by sigma surface tension times eta. Okay, and so this is always greater than 0. And so this is putting all the bells and whistles for exactly what the that's right. So this is precisely what we're told from the paper by Mahadvan on the Cheerios effect. Okay, so this is what this thing looks like. So what does this mean? Well, this means that it's always unstable. That's this. No matter what you do, this as I start pulling this thing, this immediately starts to fall apart and doesn't want to be in this stretch state. It's going to try and collapse back to its original state instantaneously, but it's going to go back at different velocities, depending on the scale of the system. Vectors in this are going to go at different velocities. And so if you say u is proportional to e to the I k x e to the t over tau, then you can pull out exactly what tau is in terms of d, and what you get is that the healing velocity is going to be 1 over k times tau. And this is the velocity that we want to compare with the expansion of the system. Okay, so the expansion of the system is going on. That's what's happening at the pulling by these pullers at the outset. This is changing the metric of this thing, so that's it's kind of independent of everything in here. So it's just trying to flow material in there as if this whole thing would just be expanding uniformly. But this is the speed at which it's going to be pulling back. And so if you compare these two things to each other, what you get is that the average length of a bit of the raft is going to be something on the order of 2 pi times nx, which is the number of particles in the original direction, times that constant d over v. And so that's what this calculation was trying to do, is give some idea of where this is coming from. And so this is, whoops, I went the wrong direction. So this is what I was just telling you about, the getting the velocity. And now you look at these two things together. And this now is the theory with all the right bells and whistles. No, everything is kind of measured. You can measure d directly, it turns out, just by watching two particles on the surface move towards each other. So it's not as if you have to just depend on these calculations, but you can measure it from the experiment. And so now we put both of those fluids together because it's a viscosity that comes in here, which is a crucial thing that changes a lot between water and water glycerol. And so this is what makes this thing move. Okay, so this is kind of our way of understanding this. It comes from having observed this kind of beautiful effect to begin with, which is the effect of these rifts forming throughout this material in a very organized and in-your-face way that then gets finer and finer and more crisp as you go faster and faster. I just I'm going to quickly jump to the bullshit line. Okay, so as I said last time, every talk should end with a bullshit line, and so this for this part, this is where the bullshit line starts. Where else do we see this kind of behavior? And so what I'm asking is, where else do we have particles that are attracted to one another, but they get weaker as they get farther apart, the attraction? Well, gravity does that. Where else do we have expansion? Well, cosmology gives us the cosmological expansion. So what I want to claim is that, oh, this simple experiment that was done, just started off simply because we thought this thing was lovely and we need to understand it. Actually, once you think about it, this is a really, an experiment that is one that you can actually start to think, oh, this is maybe how we should start thinking about the effects that happen in cosmological expansion. So again, it's one of these things which I'm wanting to get you to think, oh, here was an experiment at this level, and now we jump, and it appearing in physics at a very different scale. And so that's the spirit of what I want to you to come away with this from, that it was, okay, we analyzed this experiment. It was a fluid dynamics experiment. It was hydrodynamics at one scale, but relevant to perhaps another scale. And then the one bit I have to show is the latest thing that Kai's done is to pull this in 2 dimensions. So in both dimensions at the same time. And so this is, so this took a lot of work to make this happen. But so you see similar types of behavior here. I mean, this still has to be analyzed, but this is still in progress. Yeah.
Very interesting. That reminds me actually of another numerical experiment which I have made. That is considering the point vortices, a group of point vortices, and then exert an external expansion with that. Because point vortices also want to collide to a very small place, just like the negative diffusion. So I just got this interesting linkage.
Yeah, so I think that things like this, I'm appealed to because, we saw it here, but, gee, I think I've seen this kind of stuff before. It must be somewhere before. There's nothing so special about this that you shouldn't have seen this in many different places, but it's something that we can study here and study in a, well, concrete is not a right because there's fluid, but I mean, a very specific way. Okay, yeah. In that case, yes. Yeah. So we've done both sets of experiments, and basically nothing changes too much between the two cases, except that at the end, because they're attracted to the walls, when I pull this apart, this thing has to cut in the middle someplace. It has to separate these two things because they can't just leave gaps at the two ends. So that's one of the main differences that you see. But qualitatively, all this stuff is the same. And the stuff in the bulk is the same. I mean, so look, this is absolutely. I mean, that is, you can't. I mean, I think that makes a difference. What I was more worried about was what is dimensionality doing as you do this. I mean, we only got to 2 dimensions, but you should really do this in 3 dimensions. But you see cluster formation, and this should remind you of the cluster formation in our galaxies. That's the point. That it's relevant. This experiment is relevant to that scale.
You know how big the system would need to be in order for boundary effects to become negligible?
I don't think they ever really become negligible. That is what we're looking at, let's say in the original stuff, is once I get near the size of the system, this thing has to curve over. Once I get near the size of the individual particle, it has to turn over. And so it's only a question of how many decades do I want between those two things? But they will always, if I examine those 2 regions, my expectation is that they will always behave essentially the same. But it's just that the more decades I have, I love it, right? I mean, because I get to see that power law in the middle better and better. And so this is, we have a decade and a half or so to play with here, but that's, I would love more. We haven't done little rods. So I think that certainly the way little rods attract each other on a surface is going to be different than the way spheres attract each other. And so that'd be a good experiment to do, but we haven't done that. Okay, so I have just a little bit of time, so I'm going to quickly jump to one other experiment and try to cover this quickly. And so this is, again, going back to a granular gas. And this was done by a high school student, Peter Liu, and a postdoc, Justin Burton. And this is at energy loss at propagating jamming fronts. And so we have, if you have a particle of granular gas, you have discrete macroscopic particles, right? That is, these are individual particles. And how do they interact? Well, they basically, you don't have strong forces between them because they're the main force between these things, just hard sphere repulsion if they hit each other. And they are big enough so that they are not influenced by Brownian fluctuations in the atmosphere. And so they're hard spheres, but the one thing matters is that they do collide with each other, and when they collide, they lose some kinetic energy. So their velocity before collision is bigger than the velocity afterwards. And this is what has been called the coefficient of restitution, which is the relative speed after collisions divided by the relative speed before collisions. And so this should always be less than 1, except maybe for an active system, which could do something different, but this is what you would get for this passive system. So they leave slower than they come together. So just to show you something boring, well, this is an ordinary gas. This is what you would put on a computer, and you put a Maxwell-Boltzmann, Maxwell, who was the velocity distribution of the gas called Maxwell somebody. But anyway, it's just what you would get for the random distribution of the particle velocities in a gas. Okay, and so this doesn't have any particular structure. It's pretty random, and so this is kind of what we know very, very well. I mean, this is what we study in all of our statistical mechanics courses when we start out. But now I want to show you an image on a computer from what happens if this were a granular gas. And so this is what was work done. This isn't the first of the kind, but this is one of my favorite pictures of it is from Goldhirsch and Zanetti. This is inelastic collisions cause dissipation of the kinetic energy, but that dissipation of the kinetic energy now causes clustering in the system. That is, when you know this, that if you had two totally inelastic particles slamming into each other, they would just stick to each other. So that's cluster formation. And so even if you have a very small amount of inelasticity in here, and they come back a little bit slower, if you have enough of these things, you're going to form clusters of this kind. And so this is, I think, kind of another beautiful thing. This one was found in simulations. But you can certainly think that this would have examples from, where you have planet formation, where you have lots of dust grains that are clustering into each other, or ice flows where you have these ice things floating on on lakes, etc. Okay, so how are we told to think about this? Well, what we start off with is this idea of a temperature, which is the granular temperature, which is just 1/2 mb squared of the particles. That's basically what the temperature is of this. It's just the kinetic energy of the system. And from simple considerations of just how the collision rate at the beginning, there's a law for the uniform granular cooling, which is going to go as this is 1 plus T over tau naught over to the -2 power. Okay, so it's going to slowly start to cool down because of the collisions. That is, the kinetic energy is no longer there. It's going to start to cool down. And so we want to do an experiment with this. And so if you think about it, I'm not sure how to do this. That is, the first experiments we wanted to do was we wanted to get up onto the Vomit Comet, and which is the plane that does 0G for a while. And so you could shake this stuff and try and see what kind of things form, because if you aren't on a 0G system, everything falls to the bottom and you don't get to see anything, right? The thing just stops moving almost instantaneously, so there's nothing to be seen. And so that would be one way of trying to study this. That's the billion-dollar way to go up onto one of those things or into outer space for this. But we want to do something that you could begin to see some of these effects in the laboratory. And so I just want to show this because, again, it's one of these things that has a lot of different aspects to making the experiment work, which is something that I kind of prize about how this was done. And so over there. No. And so if you were going to do this in the lab, you'd have to get rid of gravity, which means you can't do a three-dimensional system, at least on Earth. And then you use that awful word, friction, which friction then is going to mean, I'm never dominated by the collisions. I'm always dominated by the movement of these particles on the surface in which they're on it. So you can't get rid of that easily. And so what was the solution that we used to look at this was, well, for our particles, what we decided to do was use dry ice. And so dry ice, we can get a tube of dry ice and cut it up into lots of little disks. And these disks then are very cold. It's just CO2. And what is nice about them is that if you put a dry ice pellet on a very hot surface, it floats. It's not like, I mean, you could have thought of floating on a hockey puck table, but every time you go over a little hole, this thing gets pushed back and forth. This way, it's always uniformly just melting from underneath, or not melting, but subliming from underneath this surface. So the gas is here, it has to get pushed out there, and so it's always levitated from this system. And so this is this was a nice way of getting frictionless particles on a two-dimensional surface. And so this is the idea of this thing being levitated. This is a Leidenfrost effect that you may have heard about for drops on a very hot stove, but it also works for a dry ice particle where it's so hot down below that it's evaporating this. I keep saying subliming this material here, so it has to escape. And so then you try and put these onto a table, and so you have to have a fairly large table. So you get a 2 foot by 2 foot system, and so you need this thing to be really flat. Otherwise, if it's not flat, then small little variations are going to dominate what you see in the system. And then what happens when you hit the boundaries? And so the boundaries, well, it hits the boundaries, and then you've got inelastic collisions with the boundaries, which is then, I mean, you're boundary dominated again, just as if you were hitting the floor with a three-dimensional system. And so you're going to collect all the particles at the boundary in this case. So what we did there was, instead of having it completely flat, just where the boundary was, we tilted the thing so it had a very slight slope up. So it loses kinetic energy into potential energy, but then it comes back down with the same kinetic energy as it started. So at least it doesn't lose energy at the boundaries. I mean, it translates at the boundaries, but it doesn't lose energy. Okay, so these are some of the tricks that made this thing work. And then how do you visualize it? Well, dry ice is kind of white. And so we made the table anodized aluminum, so that's black. And so it keeps it sturdier, but it also makes a good contrast so you can view this stuff easily. So this is the picture that of the apparatus. This is kind of what the idea of how it looks like, the idea that we wanted to work with this. These are these sloping sides, which as the particle moves up here, gets slower and slower, and then returns back to the rest of the material inside. So this is, now I just want to show a movie of this. So this is collision. So we're not trying to do the inelastic collapse from the beginning of the material where uniformly distributed. We're saying, okay, suppose we had gone through the half law of cooling, so it's uniformly cooled. We've gotten to those things where now we have these clusters. What we want to ask is, well, how do the clusters lose their energy at that point? So what is the end point of all of this behavior? And so what we're going to start off with is two clusters that go smashing into each other. That's the idea of this experiment now. So so this is what you see. So this thing is, we saw these two armies come smashing into each other in the middle. And then in much like what we saw yesterday with the grains hitting the target, they go in this perpendicular direction to the initial motion. Yeah. I'm sorry, I couldn't. So that's a great question, and we worried a lot about this. That is, if the particles were not smooth at the bottom. So there's a little channel for the gas to escape in one direction more than another. That could be like a little jet engine that propels this thing. So, you can arrange it so that happens. But so we did a lot of calibration on this thing to see, do the things start to move? And it tells us when it's moving below a certain velocity, then we can't trust our experiment anymore. That's the kind of thing it would tell us. But so everything that we've been telling you now is where we think we have those effects under control. But that was absolutely something to worry about. The other problem with this experiment is, gee, you have to do the experiment rather quickly because the dry ice will all disappear on you. So you order it in the morning and then you have to do it and then get it for the next day. Yeah.
It seems that half of the particles is worse in the order of circles.
So those that flipped. So they were all circles to begin with, and then some at the end have flipped over because of the collision. Yeah. Well, but they're in 2 dimensions. So the cylinders are only hitting along the circular part of this. So I'm really not caring about what's happening in the other dimensions. So I'm really only thinking about these 2D disks smashing into each other.
The plate hit from below.
Yeah. So again, you think this is easy to make this a nice uniform 100-degree thing. So well, thick aluminum conducts heat pretty well, but if it's hotter here than over here, it warps, and so that's not so good. So there's a lot of attention paid to making sure that the heat was applied uniformly across that boundary, the bottom. So there are heaters underneath this thing to keep it uniformly warm.
So those dry ice pellets melt during the experiment become smaller and smaller.
Sorry.
Will this dry ice particle cylinders melt slowly during the experiment?
Yes, they will, but the experiment is rather quick. So this was the speed at which the experiment took place. So, again, this is part of the problem of you have to do the experiment quickly, partly because of your supply came that morning and you had to chop it up and get everything clean and ready to go. But the other aspect is, if you didn't do this, if you look for a very long time behavior in this, then things start to change. So what changes in this is, okay, they get smaller. I don't care that much about that, but their mass changes. So when you have collision between 2 things, well, the mass momentum transfer is going to be different. So this was the movie of this. So I'm going to just show this movie, which is color-coded from the PIV of this so that you can see the color is the velocity. So red is the original velocity at which it's going. There are a few stragglers that were going a little slower, and then they collide. And so you can see how that behaves. Okay. So, so I'll try to hurry up. Okay, so the kinetic energy is being drained from the system, but it's being drained from the system not in this homogeneous way as it was. We started off with this uniform gas, but through the collisions of these clusters. And so what is the average thing? So this is, we do a bunch of runs, and so this is kind of what you see for what the shape is. It looks like it's a -1.5 power law. But but once we know this, we see this, we can now start go to do simulations to see if this is how this thing is going to behave. So it's roughly 1.5. I should. Okay. So how do we think about this? So this is what's called the Snowplow Model, I guess. I don't know exactly where that name came from, but we're thinking that you have 2 clusters that are cylinders, ellipses moving into each other. They start off far away, they move into each other. This region where they're overlapping is the region where they've hit each other. This region is then, we're just assuming that goes to its highest density possible. They've lost all energy in that relative kinetic energy in that region. So this goes to the jamming density in here. This is the original density outside. And this is the jamming density in the center of this, where they collide. And so you can ask, okay, so how does, if you think of this as that's the model for what is going to happen, how does this behave in time? How does the kinetic energy get lost? These two ellipses are moving at each other at a velocity v naught. So delta, this region of overlap, this is delta. That little region of overlap is going to go as v naught t. That's the speed at which they start to move over each other. Those particles interact. And so you guess, oh, well, what is the area of overlap? Well, if there are two curves, quadratic curves coming into each other, that means the area of overlap is going to be the integral of that curve, which is going to be delta to the 3/2. That's how the area varies, which means that's the number of particles that gets affected each time. So all we do now is count particles. So the total number of particles in the entire system was the initial velocity times the initial packing fraction times the initial area. And that has to be what it is at any time later. So part of that is in the jammed region, that's phi jamming times the area of the stuff that's overlapping, plus everything that wasn't overlapping yet, which is A minus AJ at the original density. So, even I can do the algebra here to get AJ in terms of whatever else is in here. I've left off all the things about how exactly what the area was, but it's going to go as the ratio of the initial density to the distance to the jamming density. And so as you get to the jamming density, I know it gets close to the jamming density, this goes up very, very rapidly. But it goes as t to the 3/2 power. It's just the same value as how delta is varying. So the energy should actually have a different power law behavior as it gets lost in this regime than you get in the initial half regime. So this is analysis of what we would think would happen given what we saw in the experiment, and it kind of more or less looks okay. But to do this, to nail it, we go to simulations where you can use a lot more particles and you can measure it more accurately. And so then this is kind of what this thing looks like in a simulation. And it does vary according to that 3/2 law that we talked about. So I'm exactly at the time when I should stop. And so so look, this picture that I have, the way I see it is I have these two ellipses, and all I was asking is, as long as it's, I want to know as long as they were randomly distributed, then the picture of how the energy is lost is really just how much of the area is being swept out by this. And so whatever that phi naught was, which could be from polydispersity or not, I mean, it is what it is. That's the one that comes into how the areas overlap. And the number and the point is that in the area you have that other density of phi j, and so that's the you're assuming everything goes to that limit. So I don't think it matters so much about what the polydispersity of of this thing is, because it's kind of a general effect. Just, I mean, what would change is if they came together as planes. That would be a different behavior. But we're assuming that no clusters are actually going to be plane-like going into each other. That always start coming in from, some protuberance in the system. Okay, so I think that's what I have to say today. So this was, I prepared another experiment, but we're not going to get to that today. So we'll come back in a couple of days. Thanks.